Subject for this week is fluid power. I've shown here the power table that we've been working on, where we had mechanical power with linear motion, mechanical power with rotational motion, and here we have fluid power. So you'll notice there's definitely a pattern emerging with how these things work. So for example, the prime mover with mechanical was either force or torque, and for fluid power it's pressure difference. So pressure difference is what causes fluids to move. And I should point out that when we talk about fluids in physics, it's not just liquids, it's also gases. So fluid power can refer to gas or liquid. We use delta lowercase p to refer to pressure difference, and typical units in the English system are pounds per square foot and pascals in metric. Pascal is 1 Newton per square meter, so it's a very small pressure unit. And we have distance or object moved. In this case, it's the volume of the fluid. So we have a volume of gas or a volume of liquid measured in cubic feet or cubic meters. Our rate has to do with volume flow, and we use this dot symbol here. There's a dot above the V to signify how fast volume is moving in time. So units for that could include cubic feet per second or cubic meters per second. Work and energy in a fluid system is given by the pressure times the volume, same units that we've discussed before. For power, it's the pressure times the volume flow, again, same units we've discussed before. And you can also think of power as energy over time. So if you come back to this energy equation, delta P times the volume divided by time, volume over time is exactly equal to V dot. So these two are equivalent. An important difference between gases and liquid is that gases are compressible. You can change the volume of a gas by exerting more pressure on it. You can compress it. But liquids are incompressible. So if you try to put pressure on a liquid, it doesn't change the volume, it just causes the pressure everywhere else in the liquid to increase. That's how hydraulic systems work. But other than that difference, most of the equations that we're going to look at with fluid power apply to both gases and liquids, as long as you're using the proper units. So first we've got pressure. Again, that's the prime mover in a fluid power system. And unfortunately with pressure, there's a lot of units that we use to describe it. There's probably more pressure units than any other quantity that we talk about. So we talk about pounds per square foot, because pressure is a force per unit area. So force divided by area is pressure. Pounds per square foot, we've got pounds per square inch. We've got inches of mercury. So one way to measure pressure is for example, air pressure we can measure with mercury by checking the height of a column of mercury. And that can be measured in inches, could be measured in millimeters. Millimeters of mercury is also known as the torr, T-O-R-R. We can look at other liquids besides mercury to measure pressure, such as water. We can look at feet of head of water. We can look at inches of water column, so it's just like feet, except it's in inches. Sometimes we abbreviate it that way, so inches of water column. And again, these are just heights of liquid that measure pressure, whether it be water or mercury. An important thing to point out about these is that we use mercury to measure air pressure. We can do the same thing with water. We can use water to measure air pressure. So the fluid we're actually using to do the measurement is not necessarily the same as the fluid whose pressure we're measuring. In the metric system, we've also got the Pascal, which is a Newton per square meter. We've got bar, which is 100,000 pascals as a bar, so it's very close to atmospheric pressure. And then we have another unit, which is actually called atmospheres. So 1 atmosphere is standard pressure at sea level for Earth, which is about 14.7 psi. So this is a good number to memorize. 1 atmosphere at sea level, 14.7 psi. And as I mentioned, there's 100,000 pascals in a bar, and a bar is just short of an atmosphere. So you can see a pascal is a very small pressure unit. And in the notes, I've given you a bunch of conversion factors between atmospheres and all these other pressure units. The ones that are most important for our work in HVAC is feet of head, inches of water, pounds per square inch, and to some extent pounds per square foot. So if you concentrate on those, you should be in good shape. These other ones, Pascal doesn't concern us much because we don't use the metric system, and mercury is more commonly used with meteorological applications than HVAC. When we talk about pressure in a moving fluid, there are 2 types we need to concern ourselves with. There's the static pressure, SP, and this is basically the pressure associated with the molecules exerting force on the walls of their container. The main component of that is due to the weight of the fluid. And then we have VP, which stands for velocity pressure. This is the pressure caused by the motion of the fluid itself. So if you stick your hand out of a car window when the car is moving, you feel additional pressure on your hand. That's due to the relative velocity of the molecules of the air hitting your hand. And then we have total pressure. Total pressure is simply the sum of those two. Total pressure is the static pressure plus the velocity pressure. We can also talk about the difference between gauge pressure and absolute pressure. So absolute is the pressure relative to a vacuum. We consider our perfect vacuum to be 0 pressure. So any pressure above that is absolute pressure. And gauge is the pressure relative to atmospheric pressure. So as an example, if we're talking about air at sea level has a pressure of 14.7 psi absolute. The A here signifies that it's an absolute pressure measurement. But in terms of gauge, because atmospheric pressure is the same as atmospheric pressure, we would call that 0 psi gauge. Now if I had some gas that was in a duct and I measured 10 psi gauge, it's relative to atmospheric pressure, so I would simply add those together and I would get 24.7 psi absolute. So in essence, absolute pressure is the sum of gauge pressure and atmospheric pressure. Next we have volume. And in the energy world, we're usually talking about HVAC systems, so we're usually talking about air or water. So typical units we use for air is cubic feet. And this is a little tricky because, of course, the volume of air can change if the pressure changes or if the temperature changes. But in general, we consider the air to be at some standard temperature and pressure, and therefore to be at a constant volume. We do most of our calculations with that assumption in mind. So that's for air. Now for water, most common volume measurement we use is the gallon. That's for water. A couple important conversions that are important to know. 1 cubic foot of water is equal to 7.48 gallons. So you can convert back and forth between a cubic foot of water and gallons. 1 gallon is also equal to 231 cubic inches. And for air, there's not really any conversions you need to worry about because we almost always talk about cubic feet. So along with volume, we talk about volume flow rate. So again, we use the dot notation to signify volume flow. It simply means volume divided by time. Anytime you see a dot, it's that quantity divided by time. So typical units for air, we have cubic feet per minute, which is often abbreviated as CFM, cubic feet per minute. And for water, we usually talk about gallons per minute, which we abbreviate GPM. So CFM and GPM are the most important volume flow measurements to be aware of. And again, in the notes, I give you some conversions. There's another interesting thing when we're talking about ducts and pipes. The volume flow is also equal to the product of the average fluid velocity and the cross-sectional area of the duct or pipe. So if I have some duct, let's say it's a square duct, and I have fluid moving through it, in this case air, I can measure the area of the duct, the cross-sectional area, that's A, and the air is moving with some forward velocity, little v, then the volume flow of that air is equal to the velocity of the air times the area of the duct. Now you got to be careful with units here. For example, if you want your volume flow to be in CFM, then V has to be measured in feet per minute, and your area of your duct, cross-sectional area, has to be measured in square feet. So the product of those will give you cubic feet per minute, which is what you want for volume flow. We've got work/energy. So one way to think about this is the work done by a fluid or done on the fluid is equal to the change in pressure times the volume of the fluid. So the energy is the same thing. On the power side, power of a fluid is equal to change in pressure times the volume flow rate. This is the important equation to know. We're going to work with this equation a lot in pumps and fans. We need to talk about how much power a pump is producing. You can look at the delta P across the pump, so the change in pressure of the water across the pump times the volume flow rate. That's your output power of the pump. Another concept related to fluids is density. And the symbol they use for this varies depending on what book you look at. Sometimes they use lowercase d, sometimes they use a Greek letter called rho, which looks kind of like a lowercase p, kind of like that. For this video, I'll just use d because it's easier to read, but just be aware that that symbol is used in the notes and it's used in other resources as well. So density is equal to the ratio between mass and volume. And at least in the English system, we in general consider it to be the weight per volume. So although mass and weight are not exactly the same thing, in the metric system we usually talk about kilograms per cubic meter, for example, and in the English system we talk about pounds per cubic foot or pounds per cubic inch, something like that. So a common unit that we use in the English system is pounds per cubic foot. For example, water has a density of 62.4 pounds per cubic foot. That's how much water weighs for 1 cubic foot. And by the way, this is for fresh water. Salt water is different. Then we have air. Again, air at standard temperature and pressure is equal to 0.075 pounds per cubic foot. And then mercury, quite a bit heavier, 849 pounds per cubic foot. So you can see mercury is over 10 times the density of water. It's a very heavy liquid because it's metal. This is the primary reason why barometers are typically made of mercury and not water, because this density is so drastic. You need a much larger column of water to give you the same pressure reading as you do for a column of mercury. So it's not really practical to build barometers out of water. So density allows us to form this equation with pressure equal to the density times the height. So for example, if I'm measuring some pressure that's equal to atmospheric pressure and I'm using mercury, then the height I need will be much less than the height of water. If I plug in 62.4 into the density, I need a much larger height to measure the same pressure reading. This is the concept between the concept of measuring pressure in a device called a U-tube manometer. It's just a device for measuring pressure using liquid. Another device that's important for HVAC is called pitot tube. Second T is silent. And this is a device used to measure pressure in a duct, and it measures static pressure and the total pressure. And I told you before that the total pressure is equal to the static pressure plus the velocity pressure, which means the velocity pressure is equal to the total minus the static. And this is a handy thing to have because it's very difficult to measure velocity pressure directly. It's usually easier to measure just static and total pressure. So if I measure those with a pitot tube in a duct, I can calculate the velocity pressure using those two measurements. Now if we have air that's at standard temperature and pressure, there's also a crude approximation I can make for velocity pressure, which is like this. Velocity pressure is equal to the velocity of the air divided by 4005 and then squared. So that will give me velocity pressure in inches of water, and I have to measure my linear velocity of the air in feet per minute. Okay, a couple of very important working equations with fluid power. Just like we saw with mechanical power, these are equations that include unit conversions right in the equation. Saves us a little bit of time as long as we're using the proper units for those quantities. Okay, for these equations, you should know that when we talk about pressure, we're talking about total pressure of the fluid. First, we have the air side. We're going to measure air power in horsepower. So air horsepower is given by power equals delta P times volume flow. Remember, that's our general power equation, but then the unit conversions are summarized as 6,356. So what this gives us is power in horsepower. Our delta P is measured in inches of water column for air, and our volume flow is measured in CFM. Same thing on the water side. Water horsepower is given by P equals delta little p volume flow over 1715. That's our conversion for water. So again, we get power in horsepower. Delta P must be measured in PSI, and volume flow must be measured in gallons per minute. So these are very good equations to memorize. It might be a little confusing at first because for air, the pressure is measured in inches of water, but for water, the pressure is measured in PSI, and that feels kind of backwards, but that's how they do it.